Hello everyone and welcome to our video on serverless computing, architectural paradigm challenges and future directions. I am Ramakrishna and I will start off with the abstract introduction and problem statement, setting the stage for why serverless computing is transforming the cloud landscape. This topic is incredibly relevant today because as more organizations move to the cloud, there is growing need for scalable, cost efficient, and developer friendly infrastructure. Serverless computing addresses many of these demands. Next, we will move to the agenda. Here, what we will cover this session. First, I will start with a brief abstract to explain what serverless computing is and why it's matter. Then we will go through a more detailed introduction of serverless paradigm. We will define the problem that traditional model faces and why serverless is powerful alternative. Next, we will dive into our methodology, which includes how we tested different architectures. After that, we will look at our implementation and then the result we obtain in the terms of performance, cost, and reliability. Finally, we will conclude with the key takeaways and purpose of future directions for serverless technologies. In next slide, we'll talk about the abstract. Serverless computing is not just a technology, it's a paradigm shift how we think about building and scaling applications. At its core, serverless computing is about letting developers focus entirely on writing business logics, while the cloud provides handless infrastructure management like provisioning servers, scaling, and availability. Two categories we'll talk about are function as a service and backend as a service. Function as a service, where individual functions respond to events like AWS Lambda or Google Cloud Function. Backend as a service, where developer relies on pre-built backend services like Firebase or Firestore. Our project explores how these models compare and how they are involved and what challenges they still face, including the cold start, vendor lock-in, security, and hybrid cloud integration. This abstract sets the stage for a deep dive into the evolution of cloud infrastructure and the emerging serverless architecture. Introduction. Let now move on to the introduction. Traditionally, cloud computing require developers and the system administrator to manually province virtual machine manage storage, scale workloads, and maintain availability, which cloud made them cheaper compared to on-premises data center. It still involved a lot of manual work and overhead. Serverless computing changes all of that. Instead of servers, developers write code and the platform runs it when needed. The benefits are tremendous. No infrastructure management, automatic scaling, pay per use pricing, faster deployment cycles. One of the biggest advantages in serverless allows developer to truly focus on building features and logic without needing to think about how to deploy and scale them. Cloud platforms like GCP, AWS, and Azure now offer robust serverless ecosystem. In our project, we focus heavily on Google Cloud, especially Google Cloud Function for event-driven function execution, Firebase for backend service like hosting, authentication, and real-time database, Cloud Run for containerization on-demand applications. However, as with any model, there are limitations, which brings up the problem statement we identified in this research. Although serverless computing sounds ideal, real world application have specific challenges that need deeper understanding. The first challenge is manually provisioning in the traditional and cloud models. Even with the automation scripts, setting up and scaling servers manually in ineffective and error prone. Secondly, while serverless simplifies deployment, it brings new concern like performance, unpredictability, especially in cold start scenarios where the function takes time to sign up. And third, there is a lack of performance benchmark. We often hear the serverless is fast, scalable, and cheap, but there are very few conformative studies across platforms like AWS Lambda, Azure Function, and GCP Cloud Function. Finally, hybrid cloud integration remains a challenge. Many enterprises want to mix on premises systems with serverless components in the cloud, but integration these environments can be complex due to networking, identity, and latency concerns. How do different serverless models perform under load? What are the trade off between function as a service, backend as a service, and event driven architecture? How do provide like GCP handle cold start and orchestration? To address this, we designed in this project methodology to study, simulate the workflow workloads, monitor metrics, and compare architecture icons. In next section, the methodology will be continued by Shashipritam.
My name is Sheshipeta. In this section, I will walk you through the methodology that is used in this research, followed by a deep dive into the implementation and key results, particularly focusing on execution latency, scalability, and operational cost. Let's start with this methodology. In this research, the understand how different serverless models perform in real-world environments, specifically FaaS, FaaS, BaaS, and EDA. In this research, they have followed a structured multi-layered approach. Step one is literature review. In this, they have reviewed the academic papers, industry white papers, and cloud provided documentation to understand the current state and limitations of serverless computing. When coming to the step two, comparative architecture design. In this, we have selected and analyzed three major paradigms: FaaS, which was function as a service, like AWS Lambda or Google Cloud Functions; BaaS, like Firebase or AWS Amplify; EDA, event driven architecture. It was built around event brokers like Pub, which is publish, and Sub, which is subscribe, Event Track, or Event Bridge. Coming to step 3, experimental setup. In this, deployed the identical serverless workloads on GCP, AWS, and Azure using 10 virtual machines per architecture, real event triggers and background jobs, and simulated both stable and burst workloads. Coming to step 4, metrics and tools. In this, the major concern was about the key performance metrics, whereas like latency, throughput, reliability, cold start delay, and operational cost. To simulate real-world latency, they have used the VPNs to mimic global user access. This gives us a fair control environment to test how serverless systems actually perform. Now let's talk about the implementation. There was they have used three identical workloads: a REST API, an image processing job, and an event-driven notification system. These workloads were then deployed across AWS Lambda with API Gateway and S3, Azure Functions with blob storage and event grid, Google Cloud Functions, Firebase, and Cloud Run using publish and subscribe and event track. For consistency, the same language runtime like Node.js, same function logic, and same event triggers were used to deploy. They have deployed like each function was triggered via API request, pub or sub events, or schedule jobs. They have generated control bursts of traffic using Locust and Apache meter. Logs and performance were captured via cloud monitoring, AWS CloudWatch, and Azure Application Insights. This setup allowed them to directly compare performance under load, idle, and burst scenarios. Coming to results execution latency, one of the main focus areas was execution latency. Like we can check how fast a function responds after it's triggered. Let me break it down for you. FaaS, function as a service. It delivers the lowest latency, averaging under 200 ms, especially for short-lived tasks. This makes it ideal for real-time use cases like chat apps, analytical dashboards, or IoT events. Coming to event-driven architecture (EDA), it came close to function as service, but added slight delays due to message queues and publish or subscribe brokers. However, it was more resilient under spikes and distributed loads. Whereas coming to backend as service, it was slightly slower, averaging around 300 to 400 ms, especially when multiple third-party services like Firebase authentication or Firestore were involved. So, function as service leads in raw speed, but EDA is better for decoupled resilient workflows. Coming to results, scalability, and cost, which are two major selling points of serverless computing. In scalability, both function as service and event driven architecture scale automatically and instantly, handling up to around 1,000 concurrent requests with no manual tuning. Whereas backend as service scale well but showed slight delays during sudden bursts due to underlying service limitations. Coming to cost, serverless billing is consumption based. That means you only pay when your code runs. We observed up to 78% lower cost when compared to equivalent VM based deployments in this research paper. For example, running a job continuously on a VM cost us around like $25 per month approximately. The same job on function as service cost around $6 per month, even including occasional cold starts. Whereas EDA also help reducing cost by using lightweight event brokers and separating compute from stateful services. One interesting insight is that Firebase on GCP gave the best balance between developer productivity and cost, especially when using FileStore plus Cloud Function plus Event Rack. So, if you are targeting fast delivery and tight budgets, serverless, especially on GCP, is a powerful choice. Now, the rest of the topic will be explained by my group member, Sai Ganesh. Thank you.
Okay, hello all. I'm Sai Ganesh, and in this section, I will walk you through the remaining part of our results, focusing on reliability, then provide a comparison between serverless and traditional architectures, and break down the differences between function as a service, backend as a service, and event-driven architecture. I will also explain how event-driven workflows power modern apps and give you a quick preview in cold start challenges and our optimization approach. Now let's get started with the results of reliability. Uh, in serverless computing, reliability means how consistently the system performs under stress, failure, or high load. We conduct reliability testing by introducing failures like delayed responses and resource continuation while sending high concurrency traffic. Here's what we found, like functional service had the highest reliability scoring, around 96% success rate under peak traffic. Even when a function failed mid-execution, returns were automatic. When comes to the event-driven architecture, came in close with FaaS because of its loosely coupled design. Components did not break the whole system when on failed. Messages were queued and read reliably. And when we come to the backend as a service, reliability varied depending on third-party dependencies. Like for example, Firebase services were stable, but chaining multiple services introduced occasional bottlenecks. On critical takeaway in that resilience in serverless is tied to how well event-driven system isolate failure, which is why EDA is a smart architecture choice for complex workflows. And now we'll continue with the serverless versus traditional architecture. Let's take a moment to understand how serverless differs from traditional cloud architecture. Like coming to the features of traditional architecture and serverless architecture. In traditional architecture infrastructure, you may manage servers, OS, and scaling fully managed by cloud provider. When and scaling manual or auto scaling with config. Uh, and complex infrastructure management continues when comes to the cost, it's continuous billing regardless of users patterns. In serverless architecture, FaaS enables granular imperial execution units and dynamic automated scaling based on workload, event-driven activation model, and when it comes to the cost, it's a paper execution cost structure. And we can also see the architecture comparison of function as a service versus backend as a service and EDA. FaaS is preferred for the custom tasks, things like image processing, webhooks, or chatbots, wherein backend as a service is great when you need speed, like using Firebase authentication or Firestore without writing much backend code. EDA is a scalable solution when your application is composed of independent services reacting to events. Thinking of it like this is the FAS is a chef cooking to order, and BaaS is a buffet, quick limited choices. EDA is a conveyor system in a factory. Each step reacts to what came before. And we will talk about the event-driven workflow. Event-driven workflows are the heart of modern cloud systems. Instead of tightly coupling services together, events are used to trigger specific functions or actions asynchronously. For example, a user uploads a file and then that triggers a function to resize the image, and then the process which then sends a message to upload the UI, and the next step is like all without one service calling the next directly. This pattern offers loose coupling, more fault tolerant, and horizontal scalability and easier debugging and isolation. On GCP, tools like EventTrack, Pub, or Sub, and cloud workflows make this kind of architecture possible and powerful. And here we'll talk about the most important topic, the cold start. Here is the introduction to cold start optimization strategies. Before I hand it over, let's quickly touch one of the biggest performance hurdles in the serverless. It is the cold start. And a cold start happens when a function hasn't been used in a while. That cloud provider must spin up a new container, which takes time, usually 500 ms to several seconds. This matters a lot of latency, sensitivity, sensitive apps like APIs or voice assistants. We address things using pre-warming and code optimization, provision concurrency. And hereby, my group member Sai Teja will continue the cold start optimization strategies. Thank you.
Thank you, Sai Ganesh. Hello, I am Sai Teja. I am talking about one of the biggest challenges in serverless computing, the cold start problem, and how we optimize it. A cold start occurs when a function is idle and a new container needed to initialize. Then introduce delay that can affect user experience in APIs and real-time systems. We evaluated three optimization strategies across platforms like AWS Lambda, Azure Function, and GCP. So a cloud start happens when a serverless function has it invoked in a while. The cloud provider needs to spin up the new container, load the function and initialize the dependencies. This add latency sometimes over 1 second. To reduce this, we used pre-warming approach. We schedule periodic function innovates each 5 minutes using cloud scheduler on GCP. So the results are like P99 latency dropped drastically from 1100 milliseconds to 130 milliseconds. That's an 89% improvement in cold start performance. So the best use cases are like APIs, chatbots and interactive UPS. These all requires fast response time and pre-warming ensure that first requests aren't delayed. And the second strategy that we're gonna talk about are container reuse and code optimization. In this approach, we tried to minimize the amount of work done during each cold start by reorganizing our code and runtime environment. We moved database connections to the global scope so that they are initialized once per container, not per function call. We applied lazy import to defer loading large libraries until they are needed. We minimized payloads by trimming unnecessary packages and optimized code structure. The results that we came across are we achieved 54% improvement in average cold start time. All platforms become more responsive, especially when the function was reused across multiple innovations. This strategy works without extra cost, make it ideal for production environment when warm and cold innovations happens frequently. The third strategy is resource provisioning and memory tuning. In this, we focused on adjusting the runtime settings to reduce cold start latency by giving the function better resource. So, increased memory allocation from 128 MB to 512 MB, reduced deployment package size using tools like Rollup and Webpack, used provisioned concurrency in AWS Lambda to pre-initialize function intents. So the cloud start time improved by 35%, especially under moderate loads. More importantly, we did not observe any major cost creep. So it's sustainable strategy for performance sensitive workload. Resource tuning is a low effort, high impact method that can be applied, especially by adjusting the platform configuration files. And the cold start optimization summary. So here is a quick summary that impacts all three strategy, like pre-warming functions, container reuse and optimization, memory tuning and provisioning. Latency is reduced 89%, 54% and 35%. The cost impact is moderate, and in the container we have neutral, and in memory we have minimal. So this optimization command makes serverless platform highly responsive and production ready. Now, let's wrap up with our key conclusion. Serverless computing, especially function as a service, has matured into a powerful architecture model. In this project, the function as a service offer low latency, high scalability, and cost effective. Platforms like Google Cloud, AWS, and Azure provide strong tooling for building event driven apps. Cold start strategies can be effectively mitigated with right strategies. Serverless is especially valuable for the application with unpredictable workload and heavy traffic and event-driven triggers. The future works that multi-cloud serverless framework, tools that allow to single feature to run on GCP, AWS, and Azure without rewriting it. This would eliminate the vendor lock-in. Advanced GCP tools, a deeper analysis of and event track workflows and cloud runs for managing containerization and event-driven function in production. And edge and IoT integration with platforms like Cloudflare, Workers, and Google Cloud at the edge. We can deploy functions closer to user, ideal for IoT devices and sensor networks. Serverless machine learning to explore using Vertex AI with Cloud Run for machine learning interfaces on-demand combined AI with power of serverless. And on behalf of our whole team, I want to sincerely thank you for watching and engaging with our research on serverless computing, architecture, paradigm challenges, and future directions. We hope this gave you clear understanding and how serverless work. This challenges is faces especially the core shard and how it is evolving with the tools like GCP Cloud Function and more. You can refer to sources listed on the slide if you would like to explore further. Once again, thank you for your time and stay curious and about the future of the cloud technology.